I've redrawn our normal distribution curve, and I've placed the population mean in there. And of course, you know that since this is a normal distribution, that's also equal to the median and equal to the mode. Several unique characteristics of the normal distribution. If we find the inflection point, that's the point on this curve where it changes from curving inward to outward or vice versa, and it's somewhere about there. And I do that on both sides. This happens to be at 1 standard deviation away from the mean. And this one, of course, is minus 1 standard deviation away from the mean. Now, we could have called that theta for population standard deviation, or we could have been a little bit sloppy and called it S, the sample standard deviation. I just use SD to indicate standard deviation. So 1 standard deviation on either side of the mean, and it turns out that that's important. Turns out that the area under this bell curve, limited by plus or minus 1 standard deviation, is equal to 68% of the area under the curve. Also, if we go out to this point, and let's call that 2 standard deviations, and likewise over here, minus 2 standard deviations, we find at this point hard to draw with these big felt markers, this area under the curve bounded by the plus or minus 2 standard deviations is equal to 95% of the area of the curve. Likewise, we could do it for 3 standard deviations, and my curve's not perfect here, of course, but somewhere out here is minus 3 standard deviations. And if we drew arrows for that, not bad for winging it, huh? We find that that area is equal to 99.7% of the area underneath the curve. Knowing those figures, 68, 95, 99.7, and that they represent 1, 2, and 3 standard deviations away from the mean, allows us to do some very interesting problems. Here's an example of a problem we could do using the normal distribution. Let's stick with pinky length for now, and let's say that for my sample that I did, the average pinky length was 2 inches, and that I calculated a standard deviation of 1 inch. Now, if we go back to our normal curve, it tells us that 1 standard deviation, plus or minus 1 standard deviation around the mean, encompasses 60% of the area under the curve. I should also tell you, and I didn't tell you this before, that the area under the entire curve is equal to 1.0, which means that one side of the curve has 0.5 and the other half of the curve has 0.5. Okay, our question, back to our question, a mean of 2.0, standard deviation of 1. The question is, what percent of people would we expect to have a pinky length greater than 3 inches? Well, let's plot that. I've drawn another curve at the bottom here. And let's see, our mean is at 2. We were given that, 2 inches. That's our sample mean. And I also, since our standard deviation is 1, I drew in the values 3 and 1, both either plus or minus 1 of our mean. And we also know something special about that, don't we? Yeah, we know that that area encompassed by pinky length of 1 and 3 represents 68% of the area. Now the question is, what percent of people have length greater than 3 inches? So what we're really trying to find is the area under that little section of the curve. And if we can figure out what that area is, that's the area with people have a pinky length greater than 3. That's our answer. But how do we know that? Well, let's see. Remember, we know what this area is. That's equal to 0.5. The question is, what's this area equal to? With the little stars. Fun little stars. Well, let's see. Since the area between 1 and 3 is equal to 68% or 0.68, this is going to be half of that. And so this area is going to be 1/2 of 68% or 34%. That's not our answer yet. We want this. Well, we know that the right side of it is equal to 0.5. So this piece is going to be equal to 0.5, the whole right half, minus the part in stars, which is 0.34, 34%. And what's that going to leave us? 16%, 0.16 or 16%. What percent of people would we expect to have pinky length greater than 3 inches? Well, that would be 16%.